Okay, so in this video, we want to consider, after looking at lines in R3, we want to look at planes in R3. Well, what is a plane in R3? Imagine viewing the three-dimensional coordinate system, so the XYZ space. As always, imagine this is the x-axis, this is the y, and this is the z-axis. The easiest way of thinking of a plane in three-dimensional space is imagine picking up the xy plane. So you have the xy plane, this infinite flat surface, and think of picking up the xy plane and moving it around anywhere in space. And if you fix it as a given point, then you have a plane in R3, in the three-dimensional space. Think, if you want, about a regular sheet of paper. Imagine holding the sheet of paper up and move it in space, and at some point you just stop and you keep the sheet of paper at that given position. And if you think of the four edges of the piece of paper as extending to infinity, you have this infinite flat surface, and that's what a plane is. But of course we can't draw the whole thing because it extends to infinity, so the idea is we usually draw a plane as a parallelogram. So normally we'll draw a generic plane as something like this, with the understanding that this flat surface has no end. So this edge would extend to infinity, same for this one, same for this one, same for this one. So there are no edges. The sheet of paper, the flat surface, extends to infinity in all directions. And that is a plane, and I'm only drawing it here as if it were horizontal, but it could be at any given angle in the three-dimensional space. Every time we have an object in space, the question is, do we have an equation involving the variables of the space, therefore here x, y, and z, that will define the points on the surface or on the object, whatever the object here is. So we have a plane. The question is, what kind of equations would we need to capture the points on this plane? Let's call this plane pi. We'll use the Greek letter P for plane. And if you think of it in the same way as a line in R3, you need two things. You need an anchor, a point on the plane, and same for the line, you needed an anchor for the line, a point on the line. And for the line, you also needed a vector that was parallel to the line, which we called the directional vector of the line. For the plane, we also need a directional vector, but as we're about to see, it will not be parallel to the plane, but perpendicular to it. So imagine a given point in space and putting your plane on top of this point. Let's call this point P naught. So this is a point in three-dimensional space. Suppose it has coordinates x naught, y naught, z naught. And now visualize your sheet of paper, this flat surface. And if you look at your flat surface, there is a unique direction that is perpendicular to your sheet of paper. And so because the plane is a two-dimensional object, a two-dimensional flat surface in three-dimensional space, there is always a unique direction in space that is perpendicular to your plane. And that will be the directional vector of the plane. Suppose that we put its initial point onto the point P naught. So given any plane in space, there is always a unique vector in space, or at least a unique direction. The length of the vector is irrelevant. As long as the vector is perpendicular to your plane, that's all you need. And we'll call this vector n for the normal vector of the plane. Normal also means perpendicular. And assume that the vector n has coordinates a, b, c. So any given plane will have a unique direction that is perpendicular to it, and all we need is a vector in that direction. Now suppose we have a point in space, given by the coordinates x, y, z. The question is, what equation would capture the point being on the plane or the point being off the plane? Suppose you have a point on the plane. Let's call this point P. And suppose that the point P has coordinates x, y, z. So we have this arbitrary point in space. And the question we're going to ask is, can we find a criteria in terms of the anchor point of the plane, P0, and its directional vector and the normal vector? Can we find a criteria in terms of these two quantities that will tell us whether or not the point P is a point on the plane? And if you look with P0 and P, you can connect them and form the vector P0, P. Call this vector U. So the vector U is P0, P. And as always, when you have a geometric vector, if you want its coordinates, you do the terminal point minus the initial point of the vector. And if we do so, well, we'll have x minus x naught, y minus y naught, and z minus z naught. So these are the coordinates of the vector u. And now think of it this way. If the point P actually lies on the plane, the vector u will be perpendicular to the vector n. On the other hand, what if the point P was slightly off the plane? Say here, then the vector u would no longer be perpendicular to the vector n. And that's the criteria. A point lies on the plane if and only if the vector it forms with the anchor point of the plane will be perpendicular to the normal vector. That is our criterion, and let's see with this criterion if we can actually come up with an equation for this plane. Let's just rephrase what we've just said. An arbitrary point in space, x, y, z, will belong to the plane, will be a point on the plane if and only if, right, this is the double-headed arrow, which means if and only if the vector u, P0, P, is perpendicular to the normal vector to the plane. And now we have a criterion. From this we can easily build an equation for the plane. Remember that two vectors are perpendicular if and only if their dot product is 0. Well, we have the coordinates of vector u and the coordinates of vector n. Let's dot these two vectors. So if and only if the vector u, x minus x naught, y minus y naught, z minus z naught, dotted with the vector n. The coordinates of n, recall, we said were ABC. So dotted with ABC. This has to be equal to 0. Now this form, and right now we have an equation, right? X naught, y naught, z naught are the coordinates of point P0 on the plane, so these are real numbers. ABC are the coordinates of the normal vector to the plane. These are also real numbers. And now we have an equation for the plane. And this form is called the vector form of the plane. This is the first form of the equation, the vector form. Let's compute now the dot product to make this look a little different, and this will be called the point normal form of the plane. So if we multiply in here, I'll put the a first, right? This is x minus x naught times a. Well, I'll write the a first, so a times x minus x naught plus y minus y naught times b. I'll put the b up front, b times y minus y naught, plus finally z minus z naught times c. Once again, the c up front, c times z minus z naught, and this has to be equal to 0. One more way of writing the equation of the plane, and this is the so-called point normal form. And the nicest one is after we multiply this out and realize that we can simplify quite nicely by making a simple change of variables. Let's multiply out here, And let's put the variables together and the constant terms together. So we'll have here ax plus by plus cz, because x, y, and z are the variables. A, B, C, remember, are real numbers, or constants, the coordinates of the normal vector. So we'll have ax plus by plus cz. And then we'll be left with negative ax naught, negative by naught, negative cz naught is equal to 0. But then we'll send these terms on the other side, these three terms, the negative ax naught, negative by naught, negative cz naught on the other side. And of course, they will become positive. So plus ax naught, plus by naught, plus cz naught. And the idea is there's no variable here. A, B, C are fixed real numbers. X naught, Y naught, Z naught are also fixed real numbers. So all this is a constant. The idea is, well, let's give this a new name. We already have A, B, C. Let's call this D. And you see now we have a really simple form for the equation of a plane. Ax plus by plus cz is equal to D. And this is the so-called general form of the plane. And this is the form that we'll usually go with. So, let's summarize. To determine a plane uniquely in space, you need two things: a point on the plane and a vector that is perpendicular to your plane. And once you have those two, you can build the equation of the plane this way. As soon as you have your normal vector, you have the coordinates of A, B, C. So you'll know A, B, and C. And to solve for D, well, you'll have the coordinates of point P naught. And because it is a point on the plane, it must satisfy this equation. And after you replace x by x naught, y by y naught, z by z naught, you'll have the value for D. So finally, the plane in three-dimensional space has an equation ax plus by plus cz is equal to D, where a, b, c, d are fixed constants, and a, b, c are quite special. They are the coordinates of the vector n, and the vector n is the normal vector to the plane, so n is any vector that is perpendicular to the plane pi. So there you have it. And the converse is also true. Any equation of this type, ax plus by plus cz equals D, will represent a plane in R3 with normal vector given by the coordinates a, b, and c. Let's consider one example of finding the distance between a point and a plane in R3. And as always, by visualizing the segment whose length is the distance, we'll find a very natural way of solving the problem. So here's what we want to find. We want the distance between the point P naught and the plane pi, where, well, let's take the plane given by the equation, say 2x minus 3y plus 4z equals say 7. Why not? And let's take the point P naught with coordinates. Let's go with 1, 1. No, that will be, let's go with 2, 1, 1. So we have this point P naught in space. We have the equation of the plane pi given by 2x plus negative 3y plus 4z equals 7. And we want the distance between these two objects. Now, as always, we have to make sure that we have here a non-trivial question. Once again, the question is trivial if the point is lying on the plane. If the point was on the plane, the distance is 0, and we're done. Well, the point will be on the plane if and only if the point is a solution to the plane equation. Let's substitute. So 2 times 2 minus 3 times 1 plus 4 times 1 gives you what? Well, 4 minus 3 plus 4, which gives you 5. And as we can see, 5 is not equal to 7. So because this point does not satisfy the equation of the plane, automatically the point P naught is not the point on the plane. So what we have here is a non-trivial question. We will have a positive distance. The question is now, how do we draw the point P naught and the plane pi? Do we have to produce an accurate sketch of P naught and pi in the standard three-dimensional coordinate system? And the answer is no. And here's why. Think of it this way. Wherever the point P naught is in space, and wherever the plane pi is in space, you can always revolve the space so as to view the picture as the plane being horizontal and the point P naught being on top of it. So you can draw a very generic picture, keeping in mind that this is what you would see after revolving the space in the appropriate fashion. So we'll draw a generic plane, always as a parallelogram. So this is our plane pi. And we'll imagine the point P naught being on top of the plane. So this is P naught, and the coordinates of P naught are 2, 1, 1. Well, one thing that we'll need on this plane will be, if you recall the problem of the distance between a point and a line, is one point on this plane. Well, a point is on the plane if it is a solution of the equation of the plane. And here we could solve for this linear equation and find all possible points on this plane, but that would be too much work. We only need one point. So let's try to find this point by inspection, and we'll call this point P. Well, how can we get a 7 with these three values? Think of it as doing 2 times 2, 4, minus 3 times negative 1 will be plus 3. That'll give you 4 plus 3 is 7. And let's take z to be 0, and we'll get a point on this plane. So let's take the point 2, negative 1, 0. Let's check again. 2 times 2 is 4, minus 3 times negative 1 is plus 3, 4 plus 3 is 7, plus 4 times 0 is 0, and we get 7. This point is a point on the plane. We could have also picked, if you want, x to be 0, y to be negative 1, that would give us a plus 3, and z to be 1 plus 4 is also 7. But any point on the plane will do, and of course then we can connect the points P and P naught and form the vector PP naught. Let's call this vector u. And as always, if you want the coordinates of a geometric vector, do the terminal point minus the initial point. So 2 minus 2 is 0. 1 minus negative 1 is 1 plus 1, 2. 1 minus 0, positive 1. And then we have vector u. There is one thing missing from our picture, and that is, of course, the directional vector of the plane, the normal vector n. It could be much longer than u, or it could be much shorter. Let me draw it shorter, but not that it matters. Suppose this is vector n. And the question is, what are the coordinates of the normal vector? Well, if you think of it, if you go back, a, b, c were the coordinates of the normal vector. So the multiple of x is 2, multiple of y is negative 3, multiple of z is 4. And so the vector n has coordinates 2, negative 3, 4. And now the question is, with this picture, how do we find the distance between the point P0 and the plane pi? Well, if you were to connect the point P0 with the plane pi, the line segment connecting the two would have to meet the plane at a 90-degree angle. So the distance is the length of this line segment. Well, if you look now, we have a vector in the exact same direction. That is the vector n. And look at the direction spanned by vector n. And if you notice, if you were to project vector u onto vector n, so construct the orthogonal projection, what you will get is actually a rectangle, right? Connect these 2 points. The angles are at 90 degrees. And if you find the orthogonal projection of u onto vector n, you have also a 90-degree angle. And now, the vector you obtain the length of this vector will be exactly the length of this line segment, which is the distance between the point P0 and the plane pi. And this is the projection of u onto n. So let us find this vector, and once we have it, the norm of this vector is the distance. Well, what we need for the projection, if you recall, is going to be the dot product between u and n dot n. So let's compute u dot n. So u dotted with n. As always, we multiply corresponding entries and we add them up. So 0 times 2 is 0, plus 2 times negative 3 is negative 6, plus 1 times 4 plus 4. So we're left with negative 2. Let's find n dot n. This will give you 2 times 2, 4, plus 3 times 3, 9, plus 4 times 4, 16. So you'll get 29. And now we can find the projection of u onto n, this vector right here, right? The vector n was the shorter one. So we can use our formula. So the projection of u onto n is simply u dot n over n dot n. This is just our scalar times the vector n. Well, we have everything we need. U dot n is negative 2 over n dot n is 29 times the vector n, 2, negative 3, 4. And now the distance will be the norm of this vector, and then we're done. Let's find the distance now. Distance is the norm of this vector, negative 2 over 29, times 2, negative 3, 4. As always, don't multiply the coordinates of the vector by this scalar, but factor this out, of course, in absolute values, so you'll get 2 over 29 times the norm of the vector n, 2, negative 3, 4. But this is just Pythagoras' theorem, so 2 over 29. The square root of the sum of the entries squared, but 2 squared, 4 plus 3 squared, 9, plus 4 squared, 16. 4 plus 9 plus 16 is just 29. And so we get the root of 29. And this is our distance. The distance between this point and this plane is exactly 2 root of 29 over 29. And that's it. And you see once again, with the help of the picture, we have a remarkably simple solution. Find any other point on the plane, so any point that solves this equation, form the vector u, project the vector u onto the normal vector of the plane, and the length of the vector obtained is exactly the distance between the point P0 and the plane pi. We could ask one more question, and that is, of course, what are the coordinates of the point on the plane lying closest to P0? Well, looking at the picture, this is the point right here. Call this point Q. And it shouldn't be too hard to see how we can compute point Q. If you're standing on point P0, you have the projection here of u onto n. Of course, if you add that to P0, you land way over here. But if you do P0 minus the projection of u onto n, you land exactly on the right spot. So this is P0 minus the projection of u onto n. And as before I leave the calculations up to you, the point P0 is just 2, 1, 1, and the projection of u onto n is just the point or vector -2/29, 2, -3, 4. So there you have it.